The motherboard is the central nervous system of a desktop computer. It provides the vital connections that allow all other components to communicate and function together. From the powerful CPU to the high-speed RAM, every component relies on the motherboard's intricate circuitry. The manufacturing process of a motherboard is a fascinating journey of engineering and precision, involving multiple stages from design to final assembly. The journey begins with a blueprint, a detailed design that dictates the layout of every component, trace, and connection. This design phase is crucial as it determines the performance, capabilities, and compatibility of the motherboard. Once the design is finalized, the manufacturing process can begin, transforming a schematic into a tangible piece of hardware. The manufacturing process can be broadly divided into several key stages. These stages include PCB fabrication, component assembly, soldering, testing and quality control, and firmware programming. Each stage plays a critical role in ensuring that the final product meets the stringent demands of modern computing. From the initial design to the final quality check, the creation of a motherboard is a testament to human ingenuity and technological advancement. Understanding the intricacies of this process provides a deeper appreciation for the complexity and sophistication of the devices that power our digital lives. Designing a motherboard is a complex undertaking requiring a deep understanding of electrical engineering, component compatibility, and thermal dynamics. Engineers start with the specifications outlining the intended use case, performance targets, and supported components. A key decision is choosing the chipset, which acts as the motherboard's traffic controller, managing data flow between the CPU, memory, and other peripherals. The layout of components is crucial for signal integrity and minimizing electromagnetic interference. Designers carefully route traces or conductive pathways to minimize signal degradation and ensure proper impedance matching. The placement of power delivery components, such as voltage regulators, is critical for stable operation, especially for high-performance CPUs and GPUs. Thermal design is another important consideration. Modern CPUs and GPUs generate significant heat, and improper heat dissipation can lead to performance throttling or even component failure. Motherboard designers strategically place heat sinks, heat pipes, and fan headers to ensure efficient cooling. They use simulation software to model airflow and optimize thermal performance under various load conditions. Throughout the design process, engineers conduct extensive simulations and testing to validate signal integrity, power delivery, and thermal performance. Prototypes are built and rigorously tested to identify and rectify any design flaws. Only after passing these rigorous tests is the design finalized, ready for the next stage of the manufacturing process. The foundation of any motherboard is its printed circuit board, or PCB, a complex multi-layered structure that provides the electrical connections between all components. Modern motherboards can have dozens of layers, each with a specific purpose. The fabrication of this intricate structure is a marvel of precision engineering. The process begins with a thin sheet of fiberglass or other insulating material, called the substrate. Copper is deposited onto the substrate using a photolithographic process, creating a pattern of conductive traces. Multiple layers are stacked and bonded together with insulating layers in between. Vias, small holes filled with conductive material, provide connections between different layers. Through-hole vias pass through all layers, while blind vias connect only specific layers. These vias are crucial for routing signals and power throughout the motherboard. Once all layers are stacked, a solder mask, a protective layer of polymer resin, is applied to the entire board except for the areas where components will be soldered. The solder mask prevents accidental shorts and provides physical protection to the traces. Finally, a silkscreen layer is applied using ink or epoxy to print component outlines, labels, and other markings on the board. This layer helps technicians during the assembly process and provides valuable information for troubleshooting and repair. Section 4, a symphony of components populating the board. With the PCB fabricated, the next stage involves populating it with thousands of tiny components, each playing a crucial role in the motherboard's functionality. This intricate assembly process requires a high degree of precision and automation. Key components include the CPU socket, memory slots, expansion slots like PCIe and M.2, power connectors, chipset, and various integrated circuits that manage different aspects of the motherboard's operation. These components come in various shapes and sizes, from large, multi-pin CPUs to minuscule surface mount resistors and capacitors. The placement of these components is critical, as even a slight misalignment can render the motherboard unusable. Modern manufacturing facilities utilize high-speed pick-and-place machines, guided by vision systems, to accurately place components onto the PCB. There are two main methods for attaching components to the PCB: through-hole technology and surface mount technology. Through-hole components have leads that pass through holes in the PCB and are soldered on the opposite side. SMT components, on the other hand, are mounted directly onto the surface of the PCB, offering a smaller footprint and increased component density. The assembly process is a carefully choreographed dance of robotics, vision systems, and sophisticated software, ensuring that each component is placed with pinpoint accuracy. This level of automation is essential for achieving the high production volumes and consistent quality required for modern motherboards. Section 5. The art of soldering. Connecting the digital nervous system. Once the components are placed, the next crucial step is soldering, the process of creating permanent electrical connections between the component leads and the PCB's copper traces. Soldering is a delicate process requiring precise temperature control and the right amount of solder to ensure a reliable and electrically sound joint. For through-hole components, wave soldering is a common method. The PCB is passed over a wave of molten solder which simultaneously solders all the through-hole component leads. This method is efficient for large-scale production, but not suitable for delicate SMT components. SMT components are typically soldered using a reflow oven. A solder paste, a mixture of tiny solder balls and flux, is applied to the PCB's solder pads. The components are then placed on the paste, and the entire assembly is passed through a reflow oven. The oven heats the PCB in a controlled manner, melting the solder paste and creating the solder joints. The choice of soldering method depends on the type of components used and the production scale. Both wave and reflow soldering require careful process control to ensure optimal solder joint quality. Factors like temperature, soldering time, and flux type play a crucial role in achieving reliable and long-lasting connections.